Good morning. We are set to wrap up chapter 16, and that means it's actually our last lecture of the semester, at least of content that we're going to be covering. We do have a review lecture that we will have before, final exams could be coming up at some point in the near future. But in any case, let's take a look at this last portion of chapter 16. We were looking at sound, and we had started looking at musical instruments. And so let's go back and review a bit of what we had talked about. We talked about string instruments, a guitar, a violin, a piano, something like that. And we said that now that we understand how standing waves work, we can go in and predict what the frequencies will be for strings on string instruments. So this seemed like a good place to pick things up. We're actually going to go back, I think I want to go back and review just a bit from what we did last semester, and that's because I brought a piano in. So we have a piano, we can actually listen to some of this stuff that we've been talking about. Now, early on with the, let's see, musical instruments started here, and kind of the first thing that they threw at us was a list of different frequencies for a set of notes. Now, these aren't exclusive to the piano. This could be a piano or a guitar or whatever. But on the piano, here's what these frequencies sound like. So they're doing what's called a chromatic scale. They're not skipping any of the notes. They're playing them all. Let me start with the C. Here is the C at, that is 262 hertz. And then, 277, 294, 310, 330, 349, 370, 392, 415, 440, 466, 494, 524. And so we had talked a little bit about octaves. We said that a piano set of notes, they're organized in a way where you double the frequency every time you step through 12 half steps. So here's a C. There is a C that's an octave higher, and those two frequencies are related. This frequency, the higher one, is exactly twice the frequency of the lower one. Here's one at half of that. So these are all Cs. These are all octaves. All right, so that gives you kind of an idea of, and again, it's a chromatic scale. Those are the 13 notes listed in that table. Now remember, we said 12 half steps lead us complete an octave. So there's one note that we start with, let's say the C in this case, and then we have to do 12 of those steps. On the 12th one, we will have doubled the frequency from that initial one that we started with. Okay, so we talked a little bit about how these frequencies are set up. We said that in what was called a well-tempered scale, what we do is we evenly space all of the frequencies. Now, we don't do them additively, we do them multiplicatively. We do them by multiplying by the same factor. So every time I do one of these half steps, lower frequency, higher frequency right next to it, that higher one is higher by a factor of the 12th root of 2. All right, and then that pattern continues. Now, what I've done, I've kind of circled on here a particular set of frequencies. I've circled the C, the E, the G, and the C prime. These make up what are called C major chord. So, I mean, if you heard these notes, you'd kind of know what that last note is going to be, right? That's such a frequently used set of pitches or set of frequencies. Is there anything special about them? And it turns out there is. these pitches are in a ratio of 4 to 5 to 6 to 8. That makes up a major chord. On this next page, I had, instead of doing a C, starting at C, I went back and started at a pitch a little lower. And the reason for that is, you know, our official tuning says that there is an A at 440 hertz. So there's an A at 440, that's sort of the official way to tune. There is another A at half that frequency, and that's at 220. Now, that would be a ratio of 2, the higher A to the lower A. So this is not a major chord, it's actually the A major chord, the major chord that starts with an A. And what we're going to do is the same thing we did with C. What we're going to do is hit the A, and then we'll 1, 2, 3, we're going to hit the fourth step, half step from that, 5, 6, we're going to hit the seventh one, 8, 9, 10, 11, 12, and then we'll hit the 12th one. And the 12th one will place us at an octave. And so the frequencies, if officially that lower A is at 220 hertz, the frequency ratio of 4 to 5 to 6 to 8 would mean that the next note, the next pitch in that major chord should be at 275, and then 330, and then 440. Now the 440 is not an issue because we set up the scales in a way where we exactly double the frequency each octave. But this well-tempered scale actually doesn't reproduce the frequency ratio that we were talking about. So this 4 to 5 to 6 to 8 sounds nice, but notice that in the well-tempered scale, the 220 is here, the 440 is there. Those are perfect 8 to 4 ratio. The E is the 6 in this ratio. That's not quite 330. We didn't write out enough significant figures to see that, but in the well-tempered scale, this is not quite 330, but it's really close. And then finally, the one that's off the most is this C sharp or D flat. That officially, if we're going to maintain the ratio, should come in at 275, but it doesn't. So why have we done this? Why have we set up a well-tempered scale where we don't quite have the perfect ratio of 4 to 5 to 6 to 8, and it's a compromise? So I don't know, were you guys expecting there would be some compromise that music would run into? The perfect ratio sounds really good. The problem is, I don't want to play just the C major chord. I want to play the A major chord, or maybe the G major chord, or the F. Well, I can't do all of those major chords and keep perfect ratios of 4 to 5 to 6 to 8 for all of them. So the well-tempered scale is a compromise. What happens is this equally tempered scale has been designed so that if we play a major chord starting with any note, and what they refer to here as playing in a different key. So if I start in the key of A, it sounds like that. If I move up, the ratios are the same, no matter what note I start with. And that means we can play a little, you know, a riff starting with some note, and then we can play the very same riff starting at a different location, and they'll have the same relative frequencies. They won't quite be integers, but they'll have the same relative frequencies. So it's kind of a compromise. Now, why an octave? And if you look at the list of notes they have here, what we're going to do for the C scale, we can just take all of the white keys. Okay, so the piano's set up kind of so that a C scale comes from just playing, skipping, which you've probably also heard. So that's considered a major scale. So in addition to the E and the G, we add in the D, we add in an F, we add in an A and a B. Now notice, when we're playing a scale like this, we don't hit all the notes. It's not what we call chromatic. We intentionally skip certain notes. So I could play the C scale, C major, and then I could shift down and play the A. All right, so chords have, 3 or 4 notes to them. Scales have maybe 8 notes that we include. Chromatic scales have them all, so nothing gets skipped. And different types of music make use of different sorts of scales. So let's continue on. So remember, musical scales, they're a compromise. All right, so we had looked at this stuff, so I'm going to go through this pretty quickly. We started out looking at string instruments and how are the string instruments going to generate these frequencies for us. Now, this is the fundamental or first harmonic, and that's the one that we're going to pay the most attention to. These are, the second and third harmonics are referred to as overtones. Now, when we play an instrument, we aren't just playing the harmonics. What I mean is, that's a C. It's not just the first harmonic that is playing. There are some amounts of overtones every time we play a note on a musical instrument, unless it's electronically generated. And when you listen to electronically generated music, just pure tones, one particular pitch, most people say it doesn't have a very warm feeling to it. So, most music is generated using instruments where we have some number of overtones. Every time a musician hits a note, it's a pattern of frequencies, not just one, that that instrument is playing. Okay, so that's what that looks like. Here is the guitar. We looked at that. I think we looked at the piano strings example. Here's another example we could use with the piano, though. They said the lowest note on the piano is at 27.5, and that's what it sounds like. So that's the lowest A. If I go an octave higher, that's the 55, 110, 220, 440, 880, 1760. Got to hit that one a few times to hear it. 3520. So those are all doubling the frequencies, and they're all octaves, is what we call them. So each of these doubled the frequencies. Now, on a piano, there's 88. A standard keyboard has 88 keys. It starts out with A0, A0, and then you just cycle through all of the notes. Now, there's an A0, there's a B flat 0, and there's a B0, but then the first C is called C1. Again, C scales get some sort of preference here. And so that's a C1, so now the numbers actually change every time they get to a C. And that's the reason that the C8 is, let's see, here is the A7, and then the B flat 7, and the B7, and the highest note on the piano is that C. Can you hear that? So the range of frequencies is between here, 27.5, and this, which is at 4,186. Okay, so hey, those are the frequencies on a standard keyboard. Now, I think we had done this problem too. I just wanted to go back and maybe have some fun playing all of those A's, all of those octaves, to see what that all sounds like. Okay, I think this example is one that we didn't do yet, so let's go ahead and take a look at this. It's saying we have a violin, and one of the strings is 32 centimeters long, and it has been tuned to play A at 440. All right, there's the A string on the violin, and it's been tuned to play at 440. Now it's saying, what's the wavelength that goes along with this. Now, there's frequency and there's wavelengths. Now, what we hear are frequencies. So when the vibrations in the air reach our ears, inside the ear there's kind of this canal that spirals around. Inside there, it's lined with hair cells. Cells that have a little hair sort of device that's kind of stuck to the side. And as the disturbances go by, the hair cells, the hairs vibrate back. They get caught up with the vibration. And that's what sets off a sensation of pitch. Just amazing that that's how this works. So it's connected to neurons, and the neurons go into the brain, and then everything gets processed. And whatever hearing is, probably something going on in the brain, is what hearing consists of. And it's that pattern of signals. So within that little spiral tube, there is an ever narrowing of the tube, and the high frequencies resonate in the narrower regions, and the lower frequencies resonate in the wider regions. So some of those hair cells will be activated depending on where the resonance takes place, and that depends on what the frequencies are. So kind of amazing, kind of the physics behind the physiology going on here. Anyway, let's say that we want to produce a frequency at 440 hertz, but we're kind of curious about the wavelengths are. Now, the wavelengths don't determine what we hear, and let's take a look and see why. So here is that string on the violin. We're back to where we're just thinking in terms of the first harmonic, that fundamental frequency. That we're going to say is the dominant frequency when we pluck this violin string, predominantly the first harmonic, 32 centimeters in length. Now, let's take a look and see how would, okay, so what we're going to do is we're going to calculate, first of all, here we go, this is what I wanted. So the first harmonic, here is the wavelength. Now we know that for the first harmonic, the wavelength is going to be given by 2 times the length of the string. That means that this string has a length of 64 centimeters. Now the frequency is 440 hertz, and we're told the string has been tuned. How did the string get tuned to that frequency? Well, what happened was the string, a certain tension was set up inside that string. We either tightened the string or we loosened the string a little bit until we got the right pitch. Now, what the tensioning is doing is it's adjusting the wave speed. So the wave speed is being adjusted. Now, even before we tuned the spring, somebody had to not build the violin, but somebody had to decide what thickness of strings to place on the violin. So at that point, we're going, the violin is this much length. That's going to give us a certain wavelength. Now what we want is we want a string with a certain linear mass density to it. And together, using the thickness of the string and the tension, we can control what the wave speed is. And if we can control the wave speed, we can determine what pitch we're going to get. Now, this is the pitch that we got, and this is the wavelength. We can use that information to say, we can calculate a wave speed. The wave speed is related to frequencies and wavelengths. If I put in the frequency that we've tuned it to, and I know what the wavelength is, it's telling us that when we tuned this, we ended up with a wave speed of 282 meters per second. So that apparently is the wave speed that we have set up. Now, what's going to happen here is that as this string vibrates back and forth at 440 vibrations a second, just think how fast that is. So the string, when you look at a string on a violin or guitar, it's just a blur, right? And it's just a blur because it's vibrating back and forth, 440 times a second. So that's going back and forth pretty fast. Now, the vibration of that sets up longitudinal waves in the air. That's sound, right? So that's the propagation of sound. And then those vibrational waves in the air end up reaching our ears. So now, the frequency in the air will match the frequency of the string, and that's because, hey, if I'm driving this thing at 440, if the string's vibrating at 440 hertz, that's going to drive the compression frequency. So the compressions are going to be generated at a rate of 440 hertz. So these two things match. Having the string vibrate at 440 hertz means that the compression wave traveling through the air and reaching our ears is also going to have that very same frequency. So the frequencies match. Now the wavelengths don't have to match. And what happens is, once we're in air, the wave speed is different. You know, the wave speed on the string was 282 meters per second, but the wave speed in the air is 343. So the wavelength will change, but that doesn't make a difference because the physics, the physical activation of those cells in our ears depend on the frequency, not on wavelength. They don't, it doesn't make any difference to them what the wavelength is. They just want to know at their specific location, how fast are these compressions going back and forth. All right. So anyway, the wave speed in the air is 343. That is coming from a different setup. It's coming from the bulk modulus, the adiabatic bulk modulus in the air, and from the density of the air. That's what's determining the wave speed there. So what we can do then is we can flip the formulas around, this one right here, and this time we're gonna solve for wavelength. So the wavelength in the air is going to be v wave divided by the frequency. I've put those numbers in. Now remember, Hertz units are cycles per second. And so the inverse seconds here are going to cancel. And what we're going to be left with are meters per cycle. We tend not to write the cycle in. We tend to just leave it as 0.78 meters or 78.0 centimeters. So the wavelength on the string was 64 centimeters, and the wavelength in the air, as that sound is propagating, is at 78 centimeters. No big deal. Wavelengths are not what are going to determine the frequency that we hear. The frequency is going to determine the pitch that we experience. All right, here is some more, here are some more nice pictures. Here's the piano, here's a guitar. And they're just kind of restating what we just talked about. They're saying that you get these strings vibrating. You want the energy of vibration in the string to couple effectively with the air. So as the string is going back and forth, you want to amplify that effect. So, the instruments are, the vibrations that are going on are often inside some kind of a box. In the guitar, you've got that sound chamber that helps amplify the sound. And so it's taking the energy in the string and transmitting that effectively to propagation through the air. Here's a flute and a clarinet. Same statement here. I guess what we're moving on to here is these aren't string instruments, so I realize that's what they're getting at here. These are not string instruments. What are they? These are not vibrating tubes, vibrating strings. They're actually tubes of air, and what's happening inside is this. So if I have a tube, and I open it at one end and I open it at the other end, what we can do with this tube is we can set up standing waves. Now within the tube, again this is open at both ends, in terms of displacement of air, this is what is considered the first harmonic, and the first harmonic has a node right in the middle, and then it has antinodes in terms of displacement. It has an antinode at the openings. Now with a musical instrument, the person who's playing the instrument actually is playing it from one of the antinodes. So on this flute, for example, the air is being blown over this opening, and that creates a disturbance. So there's a disturbance along the mouthpiece of that flute or the clarinet or a trumpet. And so with brass instruments, a trumpet or a trombone or something, the person's lips are actually vibrating, and setting a disturbance up. In a reed instrument, I guess the reed is vibrating, I know that much. And then the person playing the instrument is able to set the reed into vibration. Let's see, so there's a note in the middle, and then what we're seeing is as we move outwards, the maximum displacements are happening where the instrument is being driven, where it's being played, and then at the other end of the instrument. So the bell, open up to the air, that is transferring energy. That becomes an antinode. So this is what the second harmonic and third harmonic look like. Now notice, this looks a lot like the analysis we did for a string. And so whatever we were able to set up with the string instruments in terms of different pitches and different frequencies, we can set up with tube instruments. Now, another way to look at the tube instruments is instead of thinking this as a cylinder or a tube with a standing wave of air going on inside, we can also think of this as pressure variation. So what happens is, remember, the pressure variations are a half quarter cycle out of phase with the displacements. So if we're thinking of pressure variations, what's happening is that the large pressure variations are happening in the middle, and the zero pressure variations, the pressure nodes, are happening at the end. So that's probably a good way to think about this. The person playing this is creating a displacement antinode, but what that's ending up doing is creating a pressure node at one end and a pressure node on the other end that is in contact with the surrounding air. So, the person playing the instrument. Okay, so we've got the same pattern here that we had with strings, and that means we're going to end up with the same formulas for determining how these work. Now, let me go back quickly. I do want to take a look. Maybe we never set all these up. I know we set them up in chapter 15, and so maybe that's what you'd want to go back to see where all these formulas are derived. Okay, well, let's see what we run into as we head through. Okay, in addition to open tubes, there are what are called closed tubes. Now this is a little weird. A closed tube has one end closed, but the other end remains open. And the standing wave patterns that we get for the closed tubes are a little different. What's going to happen here is, in terms of displacement, this is a node, that's an antinode. So this distance, that's only 1/4 of the wavelength. And so the wavelength then is not twice the length, it's 4 times the length. So you have to find out about a tube instrument. Is one end closed, or are both ends open, or is one end open and one end closed? So both open are referred to as open tubes, and one open and one closed are referred to as closed tubes. Now this, because the wavelength's getting longer, it means that we're going to be able to have lower pitches. So you can try this. You can take a toilet paper tube that's been, that's left over. So take a toilet paper tube, hold it next to your ear, and you can hear the ocean right in a toilet paper tube. So what those tubes do is they tend to resonate. There's always background frequencies going on of sound, and if you hold the tube up there, the frequencies that match the particular length of the tube, those will get amplified. And so you'll be able to hear those particular pitches, which, is always a surprise. Oh, I can hear the ocean. So what you can do is you can hold up a toilet paper tube, listen to that pitch, and then put your hand over the end of that toilet paper tube. And what you'll find is that the pitch drops. So the pitch drops from when you've got one end, when you've got both ends open, to where you close off one end. So you're going from an open tube to a closed tube resonance effect. So here are some organ pipes, and organ pipes are great because organ pipes can easily be open at both ends or closed at one end and open at the other. So what would be the fundamental frequency and the first three overtones for a 26 centimeter organ pipe? It's at 20 Celsius. And then they want to do this if the pipe is open or if it's closed. So let's take a look and see. First of all, let's write down the formulas that we use for an open tube. Now for the open tube, the formulas look just like they looked for a string instrument. We got the very same formula for the wavelengths, 2L over N, where N is equal to 1, 2, 3. The frequency then, and this is what we're after. If we're designing a musical instrument, we're after a particular pitch. So the frequency here then would come down to speed of the wave divided by wavelength for a particular harmonic. So each one of the harmonics, whether it's 1, 2, 3, 4, going to have a different wavelength. We're going to generate a different frequency for that particular standing wave. Now, what that says then is that the first harmonic would be given by 2L. Let me see, let me make sure we got this right. The first harmonic would be given by speed of the wave over 2L. And then all of the higher frequencies are going to be multiples of the first harmonic. And those are just going to be all the integers. So 1, 2, 3, 4, 5, those are the frequencies that are going to get produced. Now that's an open tube, so it's open at both sides. What we saw with the closed tube is that the pattern of wavelengths are going to be given by 4L over N, but that only the odd harmonics are going to show up. Let's go back and look at that. So with this is probably good here, that's a fourth of a wavelength. Now when we move to the second harmonic, this is our closed tube, we still need to have a node, a displacement node, at this end. So that's going to continue to be the node. This end needs to be an antinode, and that means that for the next harmonic, for the first overtone, we're actually going to have 1/4 plus 1/2, and that adds up to 3/4 of a wavelength. Okay? And then this would become 1/4 plus 1/2 plus 1/2, that's 5/4. So when we take a look at these patterns that are showing up with a closed tube, we're only going to get the odd harmonics, the odd multiples. And so, yeah, so the formulas look almost the same. This is 4L instead of 2L. Those are all the multiples, all the integer multiples. These are only the odd harmonics. All right, so how different could it be? So here's the organ pipe. It's 26 centimeters in length. Again, since it's what we call a column of air, and the column here just means it's, well, it doesn't have to be cylindrical. We kind of think of it that way. So we've got this length of air inside the tube. The wave speed is going to be the speed of sound. So you know that, like with a wind instrument, you've got to warm these up. You've got to get to a point where the instrument is at the temperature that you're going to be playing it at, because you're going to keep, sending air through here, and you don't want the wave speed to change while you're playing the instrument. You want to warm it up so that it levels off at some temperature, and that means that we have control over what the wave speed will now be as we continue to play. It's going to stay at a particular value, so we got to get the instrument warmed up. Now here it was 26 centimeters, and our formula said that to get the wavelength on the first harmonic, we double that. That gives us 52 centimeters. And then the first frequency would be the wave speed over the first wavelength. That gave us 660 hertz. Now with the closing, what's going to happen is the 26, instead of multiplying by 2L, we're going to multiply by 4. So the wavelength is going to be twice as long. The wave speed is the same in both cases. And so that says the frequency then is going to be lower. It's going to be lower by an octave. So it's going to be an octave lower. Same length tube, but on one of them we closed off one end, on the other we left both ends open. Now, the harmonics complicate this too, because for this 660, I am going to double it. Now notice there was a little round off here. So this is doubling, this is 3 times, this is 4 times. So take a look at those frequencies. They don't match any of the frequencies. So you would think, with all the similarities in the formula, that some of the frequencies at least between the open and the closed tubes would match, but look, they don't. So we made 2 tubes, same length, and what happens instead is, let's see what's going on. We started with the 330 on this side, and then there was a 660, and then the next one would be the 990 that is here, and that rounded down to 989. So what's happening is we're switching back and forth. Every time we alternate back and forth, we add on roughly an additional 330 hertz. So it's kind of an interesting pattern, and that's happening because this starts at 1/2 the frequency, but then only includes the odd harmonics. So it's a different pattern of frequencies that get produced. Now here's another example. Let's see, this is a flute. It's designed to play middle C with a fundamental frequency when all the holes are covered. So woodwind instruments are, to me, a bit of a mystery. They have so many openings, so many different possible lengths from all the openings. Brass instruments seem easier because they're more transparent to me about what's going on. Anyway, here's a flute. They've closed everything, all the possible openings, so it only leaves one particular length. And that one particular length we have to calculate. So how long should the flute be if we want it to produce middle C, 262 hertz? Well, the wave speed is the speed of sound, 343 meters per second. What we can do is come back to this relational formula and say that the wavelength of the first harmonic is going to be the wave speed divided by the frequency of the first harmonic. That needs a 1 on it. 343 over 262 says the wavelength needs to be 131 centimeters. And that for an open tube, the length we would need to be 1/2 of that fundamental wavelength. And that says we want the flute to be 65 centimeters. That seems, I should have grabbed the flute, that seems like a sensible length for a flute to be. And again, what we're trying to do is, when we're using the full length of that flute, with the first harmonic, we're going to be producing that middle C frequency of 262 hertz. All right. Now, let's think about tubes, because, like with the flute, for example, that's not the only harmonic we could set up. If we go back and look at the tubes, let's look at the open ones. Let me jump back here a bit. So I'm going to go to this side. I'll do the pressure variations. Those probably look a little more familiar. Those antinodes in terms of displacement. I mean, look at both of these and think about what's happening. But here we can see that's the fundamental. This is twice the frequency. This is 3 times the frequency. We should be able to hit all those notes without changing the length of the flute. I should be able to, use that whole tube of the flute, close all the holes, and I should be able to hit these different frequencies by maybe blowing the air over the opening in a manner where, instead of setting into motion the first harmonic, what if we blow the air differently, where we set into motion the second or the third harmonic? Now, again, woodwinds to me are a bit of a mystery, but with brass instruments, this is pretty, I'm going to claim, pretty straightforward. So what if we had a tube, none of these intermediate holes here, and what if we somehow just controlled the length? So we've got one tube, and we're going to control the length. Now, the wave speed inside is the speed of sound in air, because that's what we're setting into motion. So if you start with a tube of a certain length, what you can do is you can set up different pitches. Now, I brought along with me, for this last lecture, I brought along a trombone. And so, I know a trombone's all windy, but at the end of the day, a trombone's just a tube, and the only openings are where the mouthpiece is and where the bell is. So this is the part where the vibrations set up inside come into contact with the surrounding air. And then at the mouthpiece, that's where, you know, you stick your mouth and you vibrate your lips. Right? So you close your lips fairly tightly, you force air through them, and they go into vibration. Now, what that means is, let's say that we have a certain length here, and it's designed for the lowest frequency to be able to hit an A with a pitch of 55. Let's see, where was that? I think that's it. That's the lowest A that you can hit on a trombone, on a standard trombone. They make bass trombones that have a longer length to them. So by adding length, that allows you to have longer wavelengths and hit lower pitches. So what I should be able to do then is, without changing the length, I should be able to hit all these different frequencies. And the way I'm going to do that is I'm going to tighten my lips so that when I blow air through it, that I'm resonating, I'm vibrating my lips at a certain frequency. Now that sounds weird, you know, when you're a kid learning a musical instrument, it's like, why can't that kid play the instrument? What's taking so long? And it's because you're learning to vibrate your lips at just the right frequency in order to hit these different pitches. So again, let me try this. I'm going to see if I can hit, on a good day, I can hit 8 of these harmonics. Now this one actually doesn't get used in music very much. So if you've played the trombone or you've played the trumpet, that first harmonic, you may have never been asked to play that. Usually you're asked to start with the second harmonic. So here it is. Now apparently there's a first harmonic an octave below. This is a little hard, but let me see if I can try and get that. So that's the 55, so that's harmonic number 1. I'm not changing the length, I'm just changing the vibrational frequency of my lips when I send that air through. Okay, the first harmonic's hard. That's 2. 3 and 4. 5 and 6. 7. So there. I didn't change the length. What I did was I changed, again, the way that I'm tightening my lips, pushing air through, and as I increase the tension, I'm going to get a higher wave speed, but my lips are going to vibrate. So as I create tension and tighten those muscles, my lips vibrate at a higher natural frequency as you blow air through. So yeah, we hit all of these. Now notice what is hidden inside here. You guys remember the major chords? So a lot of these are in ratios. This is certainly 2 to 1. This is 3 to 1, 4 to 1. If we go through here, let's see. There's a 4 to 5 to 6 to 8. There's one of those major chords. It's hard to focus in on that one harmonic. you know, the major chord. So without changing the length, you can hit all those frequencies. Now, how useful is it to just be able to hit these pitches? That, again, that's not very much. If we think of, you know, what notes are we actually able to hit there? Okay, I want to be able to hit more notes than that. Now, if you can, you know, if you don't have any length adjustment, then that's what you're stuck with. But trombones have a length adjustment built in. So what you can do, there are what are called 7 positions, and the 7 positions create 7 variations in length. Now, once you've got 7 different lengths to work from, and you have all of these harmonics, you can hit all the notes. So at that point, you can hit all the notes in a chromatics. Turns out that you need 7 different lengths. What about a trumpet? Maybe some of you have played trumpet. Trumpets have those valves, and so the different valves add different amounts of length. Now, how many different length variations can you come up with on a trumpet? And it's 2 times 2 times 2. 2 times 2 times 2, there's 8 different valve patterns on a trumpet. It turns out that that gives you 8 different lengths. 2 of them are redundant, so 2 of them have basically the same length. What is it? If you put down the 3rd valve, it's the same as putting down the 1st and the 2nd one. But it gives you 7 of those 8 possibilities. 7 of those lengths are distinct, and so that's how trumpets work. Same kind of pattern. So now you can, just with one length, if it's like a bugle or something, you can still play different tunes. It's just you're left with this, with a limited number of notes. With the extra length, what you find is that you can fill in all those intermediate pitches. So there you go. Brass instruments, very straightforward. Now, what we could do then for the trombone is we could predict. Now, I didn't quite do this right. It turns out that I use this in terms of A because the numbers work out so well. For the A, you can easily see the factors, the multiples of 55 as you go through. And it turns out the trombones are actually designed so that at the shortest length is a B flat, not an A. So it's a half step higher, so I apologize. I just thought that using the A as an example would be easier. What you can do, though, is if I wanted to create a tube, how long would it need to be in order to hit 55 hertz as a frequency for the first harmonic, given that the speed of the wave is going to be the speed of sound? So this is 343 divided by 55. That says that the wavelength I want to hit that low A is 6.25 meters. That says the length of the trombone needs to be 3.12 meters. Now again, I should have calculated it for B flat. In any case, I calculated it for A. It's not very different. If you get out, and I did, if you get out a measuring tape and follow the length of this, it comes in very close. Okay, so there's a few more details here. You know, how the bell flares will have an effect on exact details of what the length needs to be. But to a first approximation, hey, this is how you can go in and design your own musical instruments. All right, let's move on from this. So why do different instruments sound different? And what we're showing here is that when we play a musical instrument, when almost any sound is generated, it's not a pure tone. It's not one particular frequency. It's usually a pattern. And so that's what we're hearing from these different instruments. Here is, let's see, if this is the, I'm guessing, this is the fundamental frequency, look at the pattern of overtones of higher harmonics that show up for a clarinet. Here is a piano. The piano looks like it's, piano strings are being, the dominant effect is the fundamental frequency. And then for the violin string too, that looks very similar to like a piano. But you're getting those overtones, and that's why when you listen to it you go, that's a saxophone, right? All right, let's look at an interesting effect with sound. This is called interference. Because these disturbances are propagating out, there can be regions in space. We've got two speakers going on, and we're driving the two speakers identically. So let's say that we have these two speakers, and they're both producing the same frequency, and it's a pure tone. And what happens is there are going to be regions out, out in the air where these wave fronts are running into each other. If we have two wave fronts that overlap, that's constructive interference. So I think it's very clever here. They call the speakers A and B, and the point where we're getting constructive interference is at point C. And we can draw these wave fronts, the distance between each one of those, they're circular, or a portion of a circle. And you just draw them around the, they're actually spherical, I should correct that. So here is this sphere, and here's another sphere, and it's a snapshot that we're looking at. And so, here, and here, and here, any place where I'm seeing one of the wave fronts overlap with another wave front, that's a constructive interference effect. And they use C for constructive interference. Any place where we're halfway in between. So here is where, let's see, from speaker B, this is one of the wave fronts. Let's say this is one of the crests. But for speaker A, it's right between the two crests. That must be an anticrest. What are those called? Crest. Well, I suggested that we didn't really need to think of it that way, and I've forgotten. So there's a crest, and there's an anticrest. They're going to cancel out at that point. And so they put a D for destructive, C for constructive. I thought that was brilliant that they did that. Okay, we got a couple of loudspeakers here. Just like that picture, this is the very same picture. What they're saying is the distance between the two speakers is 1 meter. And we have measured out to some point here a distance of 4 meters. We would like to create a destructive interference effect. How are we going to do it? And so it says the frequency we're operating at is 1150 hertz. The wave speed, 343. The wavelength then is 3.35 meters. What that says is if I've got a distance along path A of 4 meters, I can take that distance and divide through by the wavelength and say that along path A, there are 1.19 wavelengths. That's how many cycles. I'm taking a snapshot. The number of cycles between here and here is 1.19. Now, if this is also 1.19, like 4 meters, I'm going to have constructive interference. So as long as the difference between the number of cycles is either 0 or a full cycle or 2 full cycles, I'll end up with constructive interference. Now what we want is destructive interference, so I'm going to take this 1.194, I kept another significant figure, and what I'm going to do is I'm looking for a distance here that will either add, in addition, an additional half wavelength, or it will remove half a wavelength. And so I'm looking for, and I wrote them down here. So if I put, I can add or subtract any number of 0.5s. These are the number of wavelengths that will destructively interfere with 1.194. These all differ by a half wavelength. And then what I can do is I can solve for dB. dB is going to be NB, the number of wavelengths, times the wavelength itself. And so all these distances would create destructive interference. Now, I came back here and I said, okay, fine, if this distance here is 1 meter, if this is 4 meters, is there a way I could find a place that's 4 meters from 1? Oh, you know what? It's not going to work, is it? I was thinking there was a way we could get this to work, but now I got to go back and recheck this. I'm not sure if we can make a triangle. We can't. So I got to cross off that last solution too. What we would need is a length of 2.32 meters, but I don't think there's a way we can do that because this needs to swing around to remain 4. This is only 1. There's no way that 1 plus 2.32 can add up to 4. And then on the other side, the next possibility was at 5.67. It's too big. It won't fit. I can't make a triangle with those lengths. I'm going to have to go back and re-look at this, but right now I'm guessing that that one won't fit either. So with the particular numbers they gave us, and again what it comes down to is creating a triangle. This side of the triangle from here to here is going to be 1 meter. This side of the triangle is 4. That means that DB has to be at least as large as 3 meters, but it can't be any larger than 5, and none of our solutions worked. So I'll go back and try making some corrections in the notes to see, but right now I'm thinking that there are no solutions to what they're looking for. Now another effect, interference effect, occurs if we have two frequencies that differ going on at the same time. So if I have two frequencies that are similar but not quite matching, what happens over time, you can see this, so they've set this up on a time scale. When this goes through 6 cycles, this is at 50 hertz, this one has gone through, when this goes through 6, this one's gone through 5. Okay, so it's a 6-to-5 ratio. And they're showing that if I start with these two disturbances, if they start out in phase, and then I allow this to go on in time. This is not a distance effect, this is a time effect. What's going to happen over time is they're going to reach a point where they're exactly out of phase with each other, and now they're right back in phase. And now they're right back out of phase again. Now if I add those two, and we've taken a look at this, if I write down the formulas for these, add them together, what I find is that initially they're reinforcing each other, but because the two frequencies are different, at some point they're out of phase and it drops down to 0. At some point, if the amplitudes start out the same, but the frequencies are a little different, there's going to become a time where they exactly cancel. Now what this creates is an effect called beats. Here is the mathematical formula of what's going on. And this is a little more detailed. So here are the combined effect from disturbance number 1 and disturbance number 2 that have different wavelength, different frequencies, and therefore different wave numbers, but the same wave speeds, because they're going through the same medium. We can use one of those trig identities to add them together. And what it gives us is this envelope where you hear this rise in pitch and rise in intensity, sorry. The rise in intensity and then a drop. Rise, drop, rise, drop. And what we find mathematically is that rise and drop in intensity is the difference between the two frequencies. So depending on how similar they are, let's go back to that example on the previous page, page before this. Yeah, one more? Yeah, this one. So what's going to happen here is that we've got one at 50 hertz and one at 60 hertz. The rise and fall in intensity will have a frequency of, the difference is 10 hertz. So that's still a pretty rapid difference. So if you were in like high school band or something and you tuned instruments, you probably listened for these beats, the beat frequency. And as the two instruments adjust back and forth, if you can eliminate the beats, then it tells you your frequencies are matching. And you can match frequencies really well using listening for these beat effects. Okay, And so let's see, in this example they say one instrument is playing at 400 hertz, but when a second instrument tries to play the same note, the same pitch, you hear beat frequencies going on. And they've told us that those beats, you count them, and you're counting 20 beats during a period of 5 seconds, and that tells you that the beat frequency is 4 hertz. And that says that, you know, if the reliable instrument is at 400 hertz, then the other one that's trying to tune to it is either at 404 or 396. Now, we don't know which one. It's either 4 hertz too high or it's 4 hertz too low. All right, we want to move on and take a look at the Doppler. And there's homework problems on those interference effects. There's a Doppler effect. You guys have probably known that if you have, you know, a police car or a fire engine comes racing down the street, and you hear this pitch, and then as it goes by, it goes, and it drops to a lower pitch, right? So does that mean right when the truck passes you, that the person, the driver inside, somehow changed the pitch of the siren? And it turns out it doesn't mean that. What's happening is this. So when the fire engine is racing through the street, that siren is producing disturbances at a particular frequency. And because the fire engine is not stopped and producing the frequencies, the fire engine is not waiting for each one of the wavefronts so that it can get a certain distance away. The fire engine actually moves forward, and so you end up with compressed wavefronts. You end up with a higher frequency. So if an object is approaching and it's making a sound, what will happen is you'll hear a higher frequency as it approaches. So that's what they're showing down here. If the fire engine were at rest, these wavefronts would be evenly spaced on both sides. But because the fire engine is moving, and because the disturbance travels relative to the air, so the wave speeds that we're talking about are not relative to the fire engine. Once those disturbances are created, they travel at a certain speed out ahead of the engine or behind, and that means that the wavefronts in front get bunched together. That's a higher frequency, and the wavefronts behind are more spread out. That's a lower frequency. If you want to find out what frequency the siren actually produces at rest, then you have to have the fire truck slow down. So when I was a kid, you know, we would get to a, you know, if you got to a railroad crossing or something, and you know, a train would be coming, the gates would come down, and I thought that was so cool that, you know, right when the train passed me, that the engineer would acknowledge my existence by changing that whistle frequency, and then I went to college and took physics and found out the engineer didn't even know I existed, right? It was just a Doppler effect the whole time. It just seemed remarkable that right when the train went by, the engineer would always change that whistle pitch for me. Anyway, I got over it. So here is the source of sound. Now, if I have a sound source that's fixed, then this is going to be a wavelength. If the sound source is moving, then the wavelengths get shortened. The frequencies go up. The wave fronts are moving at the same speed. Now, there's a bunch of formulas here that they go through. I'm going to skip these, and the reason why is there is a super Doppler formula that can be is a combination of all the effects. Now, what it takes into account is this. It can be the source of the sound that's moving, or it can be the observer. And both of these can create an effect. And so it says that the frequency that the observer observes is equal to the frequency being produced by the source times the speed of sound plus or minus the speed of the observer over the speed of sound plus or minus the speed of the source. So the tricky part on this, and they've got this listed here, this is great because there's only one formula, but you gotta get the signs right. If you get the signs wrong, it's wrong. And so what you want to do on these problems is stop and guess, before you solve the problem. Ask yourself, well, what is going to happen in this case? So here we've got a siren on a police car. The siren itself is producing disturbances at a frequency of 1600 hertz. So that's the rate at which these disturbances are being produced. What frequency will you hear if you are at rest and the police car comes by at 25 meters per second? So at first, as the police car approaches, and then later, once the police car has passed, what's the frequency on approach? What's the frequency when on separation? So let's try this. There is that super Doppler formula. The frequency of the siren is 1600 hertz. The speed of sound is 343. In this case, the speed of the source is 25 meters per second, and that goes in the denominator. So up here, you're at rest, so that's 0 meters per second. So that's 1600 hertz. And then on the numerator, I just put in the speed of sound because the observer is not moving. In the denominator, I have to, well, I'm going to try both. I'm going to try the minus sign and the plus sign. Now, when I try the minus sign, I get a frequency that's higher. Does that minus sign correspond to the siren coming towards me or the siren moving away? So you'd say, well, if the siren's coming towards me, that's when I'm going to hear the higher frequency. And so this must be when the siren is coming towards me. Let's try the other sign. Let's try the plus sign. So if I take 343 and add on 25, I get 368. This gives me the lower frequency. This must be as the siren approaches. This must be as the siren is moving away. So that's how you use the formulas. You have to ask yourself, is the observer moving? Is the source moving? Sometimes you get like this problem. You can zero out one of these. But you got to be prepared to put those numbers in and then make sense which sign is going to be approaching. Now the way the formula is written, the sign on top, which is the plus, that's for towards. That's going to give me a higher frequency. The minus sign up here is going to give me a lower frequency. That's for observer moving away. So the observer could be moving here too. The minus sign on top is for approach, and the plus sign is for moving away. That's what we just found out. Now, an example of the observer moving is you go to the symphony one night, and you're listening to this symphony, and the musicians are going, wow, it sounds really nice, but they kind of pitched a little flat. I wish we could raise the frequency a little bit, make the sound a little sharper, a little higher frequency. Well, now we know how. So if you're the symphony and you're on one of those really back rows, what you can do is you can run towards the stage. Now, as long as you keep running towards the stage, you will hear a higher frequency, and so you're going, yes, that's what I was looking for. Unfortunately, it's not a question of how close you are or how far away. It comes down to what your velocity is. So you can only run so far, and then you're at the stage, and you end up stopping, and then the frequency is going to drop back down. But as long as you're running, during that period, you're able to make the frequencies go a little higher and compensate for, the tuning of the orchestra that night. In this example, I think this is the last example maybe from the 16 chapters over 16 weeks, 2 Doppler shifts. What we're going to have is an original source creating the disturbances. The sound comes out, bounces off an object, it reflects off an object. Now the object is going to behave as a source. That reflection, the source now from the object back to, now this source was a detector. So this is like getting an ultrasound. So if you're getting an ultrasound for something, maybe they're checking your abdomen to see if all the, everything in the liver and stomach, everything looks good, the intestines. Maybe they're looking at an echocardiogram of your heart. And so wherever there's a boundary, you're going to get a reflection, and the ultrasound device both sends the sound out and then listens for the responding echo. Now they've said in this particular problem, the frequency that the ultrasound is sending out is 5,000 hertz. So I've got to do a Doppler shift this direction and then a Doppler shift back on the reflection. Now on the way out, it's the observer that is moving. And the observer is moving at 3.50 meters per second. So I added that into my super Doppler formula. On the return, it is the source that's moving. So the first effect on the way out created a frequency of 5051 hertz, and that's the frequency at which the sound is reaching that boundary, that object. It's going to reflect at that frequency. So the F1 now becomes the source frequency, and then I start filling numbers in. This time it's the observer that's at rest, and it's the source that is moving. Now I need to use a plus sign here because that's going to give me I'm expecting a Doppler shift that gives me a higher frequency. Here too it's going to be a higher frequency. So we're going to get two shifts. They're both going to be towards higher frequency if the source and the observer are coming towards each other. The second shift gave me an overall frequency of 5103. So a couple of examples. The Doppler problems are important. Take a look at the ones in the homework. I think there's some in the practice set of problems also. Okay, so let's wrap everything up here, I guess. Last couple of things that we want to talk about a bit. If I have a source that's sitting at rest, that's what the pattern of wavefronts look like. Let's say we go a little faster. When the wavefronts are shifted, I'm going to have higher frequencies here, lower frequencies here. What happens if the source is moving at the speed of sound? So if the source is moving at the speed of sound, well, the disturbances get generated, but they don't move out ahead of the source. The source is staying right up with the disturbances. What that creates is a constructive interference effect. That is the sound barrier. If you know a little bit of the history, when aircraft were first being designed to try and travel faster than sound, there were a number of engineering issues that had to be dealt with, and that's because there was this huge constructive interference shock wave that was being set up at the front of the plane. So I don't know what the details of those are, but we certainly have plenty of aircraft today traveling faster than sound. And this is what faster than sound looks like. We have the shock wave, but now the object is out ahead of the sound. So if someone's standing down here, they can't hear it. The sound has not reached them yet. So that shock wave, the angle on that shock wave, they did a little trigonometry here, and showed that the sine of that angle, if you go in and draw, we have to complete the right triangle right there, is the speed of sound over the speed of the object. And so as you go faster and faster, that angle gets smaller and smaller. Here's an example of a shock wave with water waves. The speed of water waves is not so high, so a boat traveling not too fast can create those shock wave effects at the bow. Again, here is an airplane. Here is a front shock wave from the nose of the plane. What does that look like? And then here is a shock wave from the tail of the plane being created. So the person at point C, they haven't heard anything yet. Literally, they have not heard any of the sound. The front shock wave is just passing B. So B's looking, and it looks like the jet's already gone. They're going, wow, that was so quiet. It must be one of those stealth planes. And then the shock wave reaches them, right? And then here's a person that's already experienced the shock wave. So these create sonic booms, and that's one of the issues with aircraft traveling faster than sound. We had mentioned ultrasound, so couple of slides talking about ultrasound imaging. And so here's the last image, I guess, of the 16 chapters. This is an echocardiogram. This is a human heart. It's actually upside down from what you might expect, and inverted too. So this is the left atrium and the right atrium. Here's the left ventricle, right ventricle. And you can follow these in real time. You know, I remember I had one of my kids that, you know, for whatever reason, they were following him with these echocardiograms, trying to follow up on whether his heart was remaining healthy, and it was at all of these. And in any case, when he was really young, and they would put the ultrasound machine on, and I would look and I'd go, I can't tell what's going on. And then it got to, the resolutions got so good that, you know, went in for one of these routine checkups, and they put the ultrasound on it, and you could see the heart beating. You could see all of the valves opening and closing. It's better resolution from this one that I found, this image. But anyway, it was a whole real-time video effect using ultrasound, bouncing off all these surfaces. So pretty remarkable for medical imaging. Okay, I am going to leave it there. I apologize, we went over a little bit, but we did it. We wrapped up all 16 chapters. I hope it's been kind of an adventure going through all of this. We still have some review stuff coming up. If you guys have questions, stop by.